question on number 4 here?
I love you, Enderly.
How to do the conversion? Yeah, for sure. This is chapter 1 question. Page 11, number 4. Okay, so what do you do in this craziness?
Matthew.
First of all,
Matthew.
I want to go to meters cubed. So I need to get to inches because the only way to go between SI units from English units is from inches to centimeters. Okay? So there's, you need to know, there's, the 12 inches in a foot. Okay? And what do I need to do to that thing? Yeah, it needs the whole thing to be cubed. Okay, now I know, and this is something you should really know for our exam. There's 1 inch and 2.54 centimeters. That's an exact conversion. Okay, well, and I need to do to this, cube it. Now I'm at centimeters cubed. Going to meters is a relatively easier step. I know that there's 100 centimeters per meter. Cube it. There we go. That's my calculation. So let me get another pen. Well, basically everything that I'm starring, you should know those conversions. Yeah. Usually English conversions I give you, unless it's kind of how many days in a year, how many hours in a day, stuff like that. I assume. You better know that. Yeah. Okay. Yes. Page 20. What number? 12. This one right here. Okay. C. Cuprous ion has what charge, everybody? +1. I'm feeling good vibes on that one. Mercurous. What's that? SHE2 2+, and notice the key word, overall charge. So I wasn't looking at the individual charge of the ion, I was looking at the overall charge of the ion. Mercurous has an overall +2. Hg2 2+. Okay, you can percolate, marinate on that for a little bit. Okay, thanks. Oh my goodness, yes. Page 9. This thing right here? Okay. How do you know, list the ones that are strong electrolytes. Let's just go through. I'm looking under standard conditions, so I need to know their state symbols. Under standard conditions, I'm looking for aqueous ones. And they better be aqueous ionic or aqueous strong acid or aqueous strong base. Okay. No, that's a solid. No. This is aqueous acid. Is it a strong acid? No, because not on the table. Okay. This, even if it was aqueous, yeah, it's an organic, molecular, not going to happen, and it's not really aqueous either. Okay. This one. Yeah, it's ionic. Is this a solid or aqueous according to solubility rules? So, aqueous, yeah, because of the ammonium. So you need to double check that. O2 is gas, skip it. This one, it could be an acid. Is it strong? Weak? Nope. This one, strong base. That one's going to work. Okay, next. Weak acid. Yeah. This one, according, yeah. This is an ionic compound. So this one should work as well. You probably want to double check the solubility rules. You see that sulfates are always aqueous, so that one should work. Is that okay? Okay, next, yes. 14 on the same page. Oh gosh, okay. Can I save this for a little bit? Because I'll come back to you. Okay, next, yes. Page 8. Number 12, this one. Which one did you think it was? Or were you not sure? Not sure at all. Okay. So, what you're going to do is remember Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. Okay, so this would have Avogadro's number times 8. Is that okay? Because there's 8 of sulfurs. This would have 2 times Avogadro's number times 4. Because there's 2 moles. Is that okay? So 8 again? Okay. This would have 4 times chlorine. So 4. Chlorine molecules. Oh wait, what does a chlorine molecule look like? Cl2. Okay, so this is also 8. 4 times. Is this too crazy that I'm not writing it down? Should I write it down? Okay, okay. This is 3 times Avogadro's number times 3. 9. This is the highest so far. And then this is 8 times 1. So it's really D looks like the highest. Because it's 3 and there's 3 in each of them. So it's going to be a total of 9. Okay, if that doesn't work, let me know. Yes? So I'm just trying to go fast because you all are crazy and lots of you have questions for some reason. That's awesome. What number? Okay, this is the one I was referring to that I was expecting somebody to ask me eventually. Okay, let's work on that one. This is page 51, number 21. Let me write down the question first, then we'll decide how we want to solve it, okay? So, you have X milliliters of wine. That's 0.0030 molar sugar, okay? To that, you're going to mix in 20 milliliters of wine, which is 0.00010 molar sugar. So you're adding those two. Okay? To that, you're adding 30 milliliters, which is with 0.0020 molar sugar. Okay? Once you've done all that, that's an equal sign. You get 0.0015 molar sugar. Okay? What's the volume, anybody? Of this result? Yeah, X plus 20 plus 30, 50 plus X. Okay? Milliliters. All right. Now, usually when you're mixing things together, you might think the dilution formula. Okay? But it doesn't work when there's so many things going on. So you need to go back to the major concept, which is moles initial is moles final. That one will work here. And you'll see if you look back in the reader, I highlighted that formula because of this problem. Okay. This is from a previous final exam, and so I wanted to get you ready for the final. That's why it's here. So you would just need to say, okay, I can find moles final. I'll put it out here on the right. That would be the molarity times volume. Is that okay for the final? Okay, do the same for the initial, but there's just a lot more. X times 0.0030 plus 20 times 0.00010 plus 30 times 0.0020. One unknown X. Is that all right? Cool. Next. Yes? Page 50. All right, back one. That's easy to find. What part? Of course, the last one. Okay, this one right here. Page 4 and 50. All right, how do you do this craziness? I look for what I recognize. Okay, so for example, what's the charge on this SO4 entity? -2, we call that sulfate. This we call water, it's 0. This is carbonate, -2. Okay, so I'm doing ones that I recognize. Now, once I have all that, I'm going to set up a little formula. So I'm going to need to move this out of the way. Let's go back. A little bit more thinking will save us a little time. Okay, here's the craziness. The carbonate is -2, right? That means everything in the brackets is everything in the brackets plus 1. Because there's 2 of them. for example, Na2CO3 would be an equivalent. If this is -2, there's 2 of them, the sodium itself is +1. Got that? Okay, now let's go to our scratch work here. Move this out of the way. So you would go now, I'm just caring about what's in the brackets, which is, I've now determined is +1, is iron plus the sulfate, which is -2, plus 5 waters is 0. So iron is going to be +3. Is that okay? Wow, so easy. No, I'm just messing around. I know it's hard when you first see it. Okay, cool. Yes? Page 38. 38. This one right here? Yeah, okay. Oh yeah. If you see a problem that has like density and percent mass, and volume and mess like that, it's a combo problem. Okay, so I need to write this out separately here. Even gives me the molar mass, 178.95 grams per mole. I know that this is 50.6% by mass. I know the density is 1.549 grams per milliliter. Okay, so what volume of stock solution, that's the stock. This is stock, that means what you buy or what you get from the stock room. What volume of stock solution, question mark, is needed to make, so you're making 400 milliliters of 0.25 molar solution. So here's why it's a combo problem. If I write out, you see it kind of looks like a dilution a little bit. M1V1 equals M2V2. Let's get a different color pen now. Here's V2 right there. That's the final volume. Here's the other molarity. V1 is what I want. That's this, the volume I don't know. But here's the problem with the molarity. That's the molarity, whatever that is. Okay? So you need the first part is a conversion. After you complete the conversion, then you use the dilution. Is that okay? All right, so what if I just do the conversion and leave the dilution to you? The dilution is the easier part? Okay, so the conversion part now. If you have a conversion problem, it's a pretty normal problem to have a percent mass, a density, and a volume. Or, yeah, a density and a percent mass, I guess I should say. How do you do that? Well, the 50.6% mass means there's 50 grams of the solute for 100 grams of the solution. The solute is the manganese sulfate, or I should say, manganese nitrate. The manganese 2 nitrate, that's a solute. Okay? So that's what that means. Okay, now what you're going to do is take the density. There's 1.549 grams per milliliter, right? The density is always a solution density. So if you look in the problem, it just says the stock solution has this density. So you're going to notice what cancels this right here. Cancels. So now I'm grams of solute per milliliter of solution. Okay? Okay, next step. Let's get rid of this grams of solute, because in molarity I need moles on top. So it's 178.95 grams per mole. And that grams of solute is now gone. So I have moles on top. I'm almost there. Okay? What do I need to do down here? One last step and convert the milliliters to liters. So I multiply by 1,000. Is that okay? It's always this. You take the percent mass, multiply by the density, divide by the molar mass, and convert. Okay? Yeah, it's a pretty common conversion. Okay, next. Yes, way back in the sweatshirt.
Page 32, question 10.
32. 32, number 10. Oh, the Bezium.
Yeah, I was confused between gram per mole and AMU.
Say it one more time.
I was confused between using gram per mole and U. Which one should we select?
Oh, and the question is the grams per mole for U. Which one should you stick with? Really, I guess you used grams per mole twice there. What did you get as an answer? A, B, C, D, or E?
The answer is B.
Good. But you weren't sure about C?
Yeah.
Okay. Yeah, if you end with the units you start with. So if you start with U, end with U.
Okay.
Yeah,
What's the difference between both?
U is a what's the difference? U is a microscopic unit, meaning if the atom or the molecule itself, Bezium, or the element, is 223.25. But a mole of Bezium is 223.25 grams. So the grams per mole is a macroscopic unit. Usually with isotopes, since we're talking about just individual elements or atoms, we're talking about U. But in every other problem in Chem 2A, until you get to Chem 2C, I guess, we're going to be talking about grams per mole because we're talking about macroscopic.
Okay, but gram per mole and U are equivalent units, right?
They're equivalent in that you can tack either one at the end, but you should be sticking with the unit you start with. Meaning this problem, we're just sticking with the element itself.
Okay.
Yeah.
Thank you.
Good. So, nothing more than that. That's it. Yes? Page 8.
I don't know if it is in the I don't know if you need to see it
Okay. Number 8. Okay. Oh, no. This one. Right here. The Tears of Joy. That one. Okay. I want to encourage that quarter during the exam. Okay. All right. So this, what's the molarity? They give us like mass. Let me write all the stuff they give us down. Grams. Assume that in addition to the 5 grams of pure water, a tear of joy, so here's my tear, has 6.0 times 10 to the minus 7 grams of, so you're crying salt and water at the same time. Assume the density of the mixture is 1.0 grams per centimeter cubed, so essentially that of water. What's the tear's molarity? So this is just a conversion problem, okay? We're going from masses and things like that to molarity. So we just need moles per liter. Okay, let's do that. The mole of the solute, so I need 6.0 times 10 to the minus 7 grams on top. That's the solute, or salt. I'm going to multiply this by the molar mass of salt, so I'll have you look that up. Okay? And then, so that'll change to moles on top. On the bottom, I need liters. Okay? Well, and that's liters of the solution itself, which is a teardrop. Well, right now I only have grams. Okay? But I can convert this to a volume unit using the density. If I write it like this, density is mass over volume. So I have density and volume, I'm just multiplying them to get, or I have mass and density, I'm kind of rearranging to get volume. Is that okay? Yeah. But I don't want centimeters cubed for molarity. So I need to do a couple conversions. This is still in the denominator, by the way. Okay. I need to do a couple conversions to get to, where am I going? To molarity. So a milliliter is equal to a centimeter cubed. And then 1,000 milliliters per liter. So basically dividing by 1,000 in the denominator. Is that all right? Okay, cool. Yes? Awesome. Why do I only use the grams of water here and not the whole solution? Yeah, it's too small. Meaning you can add that number down here, that's totally fine. But try it on your calculator and you're going to get back the first number. Is that okay? There's a second reason you could argue is the sig figs. The error, that's way out of the error bounds of this one. Because it's way in the millionth place or something like that. Or further. Okay, yes, and I'll go up there. Yeah. You want the sodium chloride mass where? In the denominator? Because, why not put in the denominator? Because you need the solution mass here, which is the solute plus the solvent. So you need both of them down there. Really. It's always the total in the bottom or the volume section of the layer, and that's right. Yes? 36. Yes, exciting. Number 16. That one? Cool. Can you tell me what confused you? You're like, what the heck do I do right now? You don't have the percent of each isotope? Cool. Yes. You were thinking smartly, but not the direction I was hoping. Yes. What do I do? Yeah, just look on the periodic table. That's all I wanted. I just gave you extra information. The real question is, find the atomic mass of chlorine. The first part was just for fun. Yeah. Cool. I guess it worked. Awesome. Yes. But you'll never miss that one again. I was so proud of this question I thought. Okay. Page 12. 60. 16. Okay, got it. This one? Tryptophan? Yeah. This I did this in class, right? No? What? Okay, I don't believe you all, but I'll pretend that's true. Number 12. I should have done this at the end of chapter 2. So when we first started chapter 3. Okay, so how many carbon atoms? First let's count the carbon atoms. How many did you get? Anybody? 11, 6, 7, 8, 9, 10, 11. Sounds good. So you would go, there's 2.3 moles, I'll put of tryptophan, T. And there's 11 moles of carbon for every 1 mole of tryptophan. And then I want carbon atoms, 6.022 times 10 to the 23rd atoms of carbon per mole. Look okay? Okay, cool. Who's next? Yes. And then we'll probably just a couple more, and then we'll close up shop. You have to go home and watch TV. 10? 10, number 20. Yeah. This one right here? Yeah. Okay, this is one of those percent. Yeah. Okay. Page 10, number 20. A plus 2B goes to C. You start with 50 grams of this. You isolate 15 grams of C. If you know that the molar mass of B is 300 grams per mole, and the molar mass of C is 67 grams per mole, I want to find the theoretical yield and the percent yield that is represented by the above. Okay. Right, did I miss something? No? Okay. So, I want to find out, they're asking me how much C did I make. It's not 15. What's 15? Yeah, the isolated actual. Okay, so I'm going to this way and I'm looking for mass, but not that mass. So this is one of those variants I told you about. So you go 50 grams, change the moles first, step 1 to the moles, 300 grams. And then there's 1 mole C for every 2 moles. B, C is 67 grams per mole. And this should be the grams of C. I'm going to take, let's go to a different color here. I'm going to take this number and put it in the following equation. 15 grams or whatever that is, grams of C times 100. So the grams of C is part A, or the theoretical yield, and then this calculation in black here is the second part. Is that all right? Okay, cool. Last question. Yes?
Page 11, question 2.
11. This one.
Yeah.
Okay, cool. What's the deal here?
I was confused which one to use.
You were confused which one to use. Okay. When solving empirical formula combustion analysis problem. Oh, I can see why you're confused. Which of the following laws are needed to solve the problem? I was looking for the law of multiple portions because you need to divide by the smallest number.
Okay.
What else did you think was a possible answer?
Conservation of mass.
Yeah, that's possible. Yeah, usually the way we presented the conservation of mass is a little bit more, what part, do you remember what part of the problem you would need the conservation of mass? When you're solving for? Solving for the oxygen, does this have oxygen? It's hydrocarbon, there's no oxygen.
Okay.
Yeah, is that cool?
Yeah.
Yeah, so I see what you're thinking, but this only has hydrogen carbon. All right, cool. Well, I had a fun time. I hope that was helpful. We'll have one more class before. What was your question? Oh, yeah, I have to do your question. What page was it on? Page 17. I do have to do your question, that's right. No TV for you. Okay, people are freaking out here in the front. What? This one. Okay, let's do it. So if you want to see in this balancing one, you can stick around for a few minutes. This is just one of those like the others. Okay. This is awesome. Okay, now some of these are going to be a little bit easier. So for example, where there's A, B, oh, let's start with what we know. I gave you 2. That means I thought it was really hard if I gave you a couple of them. Okay, are any of these variables only appear once? Carbon appears here, right? Where else does it appear? Just here, right? Here and here? So I know what A is. What's A? Just 6, right? 36 carbons on each side. Okay, hydrogen, does it appear in a bunch of places? Oh, just here, right? So what's C? 355, right? Oh gosh, this is so easy. Okay, and now is where it gets crazy, right? There's so many oxygens, I think, yeah. Okay, so I'm gonna go, hopefully you have this written down. Can I take away the equation? Okay. So now here's where you have to get a little bit crazy. So now let's just pick some of the elements and kind of go through. So I'm just picking the element iron. Okay. Iron appears, oh, okay. Hold up. Iron only appears these 2 places, right? So then what's D? Oh, so this is so easy. Okay. Is that cool? Now, do any of these others only appear one other place, like K, sulfur, nitrogen? Yeah. Do any of the others appear only one place? Nitrogen is here, right? Okay, so what's the G? Let's see if that works. If that's 36, there's 36 nitrogen, oh my gosh, we're almost done. Okay? We've got potassium, nitrogen, so let's see. Where are all the sulfurs? Besides these 2 places, what other sulfurs do we got? Oh, we've got 2 here and here. Is there anything else that just appears one more time in a variable location? Chromium is in 2 variable locations. You see that, B and E? All right, now I need to go to the other page. I think I got all the easy ones. Okay, let's start with chromium because that looked really easy. Chromium, is it okay if I write 2, what was that, B equals 2, what was that variable? E. Is that okay? So B equals E, whatever that is, so I could kind of B, it's now B, which was E. Okay? All right, is there anything other element that it appears not too often? Did we do hydrogen already? Did we do sulfur? Let's do sulfur. So sulfur appears in the first equation. How many is in K4 iron SCN? How many sulfurs are there? 6 times 6, right? 36. Sulfur is always also with H2O. What's the coefficient for H2SO4? Oh no, it was this one. Okay. What's 355 times 2? Oh no, times 1, right? Oh, sweet. 355 equals, where else does sulfur appear? Okay, I gotta line this up. There's how many sulfurs here? I'll move this in a second. There's 9 there. How many sulfurs here? 3B, right? Is there any other sulfurs? Oh yeah, plus F. Oh wow. What's that minus that? It looks like... Okay, so what's that minus 9, I guess? 300... Okay, that sounds good. 3B plus F. Okay. What element have we not worked with yet? Any element here that we have not messed with yet? We already did potassium? Yeah? We didn't do potassium yet? Oh my gosh, that's an easy one, I think. I hope. Okay. Potassium, there's 24 plus 2B equals, what the heck is it? 2F. Does that work? Plus a 36. Okay. Now I forgot what I said. It's, wait, what was the first number? 24 plus 2B, 2F. Okay, I'll trust you. Plus 36. Oh, cool. I have 2 equations and 2 unknowns, right? Okay, so this is 2B equals 2F plus 12, right? Or B equals F plus 6. Now I'm gonna combine them. Find B and F. That and that. So this is right too, yeah. So I will plug in for, it doesn't matter, B, whatever. 382 equals 3B, 3F plus 18 plus F, right? So that's 4F equals, 360 something. 4. What's that divided by 4?
91.
81? Sounds good to me.
91.
Okay, sounds even better. Okay, so what's B? Okay, cool. So, we're done. Cool. How long did that take us? We should have timed it. 5 or 6 minutes. Oh my gosh. Is that worth the 4 points? It's up to you. Alright, now